Welcome to today's webinar on the topic of advanced system simulation for future marine propulsion concepts. First, I want to introduce myself. My name is Maximilian Sommer. I will be the moderator for today. I'm in the Marketing and Communications Department of AVL Simulation Technologies, and I've been with AVL since 2014. Let's start with some housekeeping. This is a live webinar. Of course, we will record this session, and within the next couple of days, you will get an email with a download link so you can watch this webinar also on demand after it's done. Another important information is our Q&A session at the end of this presentation. So please feel free to post your questions in the chatter in WebEx so we can collect them and discuss them at the end of this webinar. The chat is open throughout the entire presentation. So if something comes up, just type it in and send it to us so we can collect them. I'm very happy to introduce today's presenter, Mr. Robert Strasser, a lead engineer for real-time and system simulation with AVL. He went to the University of Technology here in Graz, joined AVL in 1997 and had quite a few stops in his career within AVL and quite a few positions. He started out as a development engineer, moved to project management, and now Robert is the lead engineer for real-time and system simulation in AVL's business unit High Power Systems. With his team, he deals among others with the specification and optimization of systems for marine, railway and power generation applications. I'm very glad to have you here, and I would like to pass over the microphone and the presentation to you, and I will talk to you soon in the Q&A session. Welcome, Robert.
Thank you very much for the introduction. Ladies and gentlemen, AVL provides solutions for all customer segments, for passenger cars, two-wheelers, racing applications, construction, agriculture, commercial vehicle. Besides, AVL has numerous services in the area of large engines and deals with locomotives, marine and power plant applications. AVL's main areas of activities include powertrain engineering, simulation, as well as development of simulation software and testing. AVL is well known as a partner in the automotive world. However, AVL has a business field dealing with marine applications and offers different services and products for marine, such as the development of combustion engines for marine applications, the condition monitoring system AVL EPOS, system integration, retrofit solutions, field support, and the development of future propulsion concepts. Today, I would like to present our activities regarding system simulation for marine applications, which is an important methodology for supporting system integration. We all had to rise challenges in the last few years, and we will have to master even greater challenges in the future. The energy market is a challenge as the prices for oil, gas and electricity are changing, and they influence our work significantly. Catchwords are dual fuel engines, conversion to gas operation and hybridization. The legislation forms our boundary conditions for developing new products. Emission control areas will be extended. There are very strict local legislations and low sulfur fuels, limitation of greenhouse gases are major topics. The environmental awareness of our customers and our environmental responsibility are also important drivers for introducing new technologies. There is high attention of public and politics. In the last years, we successfully introduced technologies such as Miller timing, EGR, SCR, two-stage turbocharging to the market. Dual fuel engines and hybridization are almost state-of-the-art technologies today, even for the marine industry. AVL is now working on many new technologies: fuel cell technology, battery technology, electronic control, electrically driven turbochargers, new ignition technologies such as microwave or laser ignition, new after-treatment concepts, and many more. Ambitious goals must be achieved by 2030. The carbon dioxide emissions have to be reduced by 40%. The NOx emissions should be 80% lower. Here we need completely new approaches. It is not enough just to optimize engine performance or optimize single subsystems. New concepts are required, comprising the entire propulsion and energy system of a vessel. AVL customers are no more only engine OEMs and engine suppliers. In case of marine applications, we have shipyards, shipbuilders, ship owners and operators, propulsion system suppliers, control suppliers, but also classification societies as customers and partners. The partners developing a new product or operating an existing system have various challenges and tasks listed in this figure. Shipyards are responsible for system integration, and they want to improve the total cost of ownership for their customers. Engine and component suppliers want to introduce high-efficient, reliable products, enabling lowest emissions and best energy efficiency design index. Ship owners want to do route optimization, maintenance planning, or they want to renew their fleets. Last but not least, classification societies are interested in concept proofs, virtual homologation, model-based validation of systems, or fail-safe investigations. Most of these different tasks can be supported by system simulation, virtual system integration, or model-based development approaches. We need technologies which ensure the compliance with future environmental legislation. There is the combustion engine technology, for example, two-stage turbocharging, the increase of the peak cylinder pressure higher than 300 bar, variable compression ratio, variable valve timing, LNG, gas engines, exhaust gas after-treatment technologies, or friction reduction. Hybridization is interesting in many areas of marine application. Here the combustion engine has a new role with changed boundary condition and operating strategies. New energy sources, fuel cells, hydrogen and alternative fuels, energy storage systems and innovative propulsion systems can also contribute to an efficient and clean operation. And there are new methodologies such as virtual system integration, advanced system simulation, model-based development and virtual testing. They support the development and help to optimize the overall propulsion and energy systems of ships. Virtual reality plays an increasingly important role in the development process. There are catchwords such as virtual system integration, system simulation, and model-based development. Today I would like to show you that these terms are not abstract terms and that system simulation and model-based development approaches are helpful tools for developing new marine propulsion system technologies, and how simulation and model-based development activities can support testing. So I will give you a brief introduction to system simulation and its tasks. Then I will show use cases, and subsequently I would like to explain model-based development and virtual testing. First of all, I would like to explain system simulation. According to my definition, it is the description of the relationship between elements or components by appropriate models. I would like to explain it by means of a small example from biology. If we have a predator-prey relationship, for example with foxes and rabbits, this relationship can be described by the so-called Lotka-Volterra equations. Two ordinary differential equations are coupled. The number of foxes and rabbits are variables, and the growth rates of each population and some parameters are describing the interactions of the species. We can set up a simulation model describing the situation and simulate it. And based on the chosen parameters, we can achieve thousands of different results for the development of the fox and rabbit population. Only a few cases are shown in this figure. But there's a huge variety of different results depending on the boundary conditions and the parameters. Whereas in the example with the foxes and the rabbits, there are only two subsystems, for the system simulation of a marine hybrid application, many single models, subsystems and components of different domains with different characteristics can be used for the purpose of an overall system simulation. With an appropriate tool, it is possible to describe components and to describe the interactions between components and subsystems. The multi-domain system simulation allows the optimization of the energy management and investigations on the interactions between various subsystems. Large engine applications are generally characterized by high system complexity, as there are multiple propulsion and energy systems comprising different domains. Especially in view of increasing demand regarding new technologies and hybridization, system simulation and model-based development approaches help to understand and to optimize overall systems. There are numerous tasks of system simulation in the development process with the aim of supporting concept decisions, the specification of components, but it is not enough just to find the best and optimum components. It is necessary to develop the optimum operating and control strategy. The main objective of system simulation is the improvement of the operational excellence. It should support new ship design, optimize performance and the operating strategy. It should help to prevent errors and detect failures in a very early stage. Damages should be avoided and the reliability and availability has to be improved. System simulation and virtual testing is useful when tests are too expensive to be performed, when there is limited component availability, and when the effort for testing and the number of variants are high. System simulation and virtual testing is also useful when the risk of tests is high. With virtual approaches, there is no danger of exceeding limits and damaging very expensive and individual components. System simulation is a valuable methodology when tests cannot be performed in reality. For example, if extreme boundary conditions are given or when worst-case scenarios should be investigated. What are the benefits? There are three main benefits. The cost reduction. Virtual tests are much cheaper than hardware tests. Early detected failures reduce cost and the operational expenditure can be reduced by optimization. With a clear reduction of development time, due to a shift of development activities, for example controls development or calibration, from the testbed to hill systems or to the office, in an early project stage, the overall development time is shorter. A very important aspect is the quality improvement. As tests can be performed virtually, which cannot be performed on testbed or in real life, virtual testing is a clear measure of quality assurance. Fail-safe investigations can be easily performed and systems can be virtually validated. That means that costs can be saved before they even arise. Let's have a look on the AVL development process of any large engine application. You can see a schematic with three main events: the concept decision, the start of the prototype assembly, and the commissioning. The virtual system integration is embedded into the entire development process and even in the real operation after commissioning. It starts with concept simulation and performance analysis, makes use of various model-based approaches such as model-based control system development and model-based calibration, and continues during operation, for example with simulators or model-based condition monitoring. The idea is that one model should answer all the questions of all the development partners, suppliers, shipyards, classes, and operators. An interesting aspect is the enhancement of system boundaries. Usually we have the focus on the engine or single components of the propulsion system. However, the engine is embedded into a propulsion system, maybe a hybrid installation, influencing the operation and the performance of the engines. And the propulsion system is embedded into an overall system, for example a ship with additional power consumers, operating strategies, and control systems. Last but not least, there are ambient and weather conditions, navigation, routes, specific operating and use cases which have effects on the performance of the propulsion system and the boundary conditions of single components. The appropriate system boundaries have to be chosen in order to consider all relevant effects for the given task. We mainly use Cruise-M as a multi-domain system engineering simulator. The name of the tool, Cruise-M, might be misleading for marine applications, as the tool has its origin in the automotive world. However, it is not only possible to use it for the simulation of cruise liners, we can use it for all types of vessels and ships. Cruise-M is an open and integrative platform with a multi-physical approach, which allows a consistent plant modeling through the entire development process with scalable models. Besides, we use AVL Model Connect. This is a neutral model integration and co-simulation platform connecting virtual and real components. With Model Connect, it is possible to connect simulation models created with different leading simulation tools to a consistent virtual prototype, and we have also full support for industry interface standards such as the so-called Functional Mockup Interface FMI or FMU. For more information about Cruise-M and Model Connect, you can go to the website avl.com. Please search for Cruise-M and Model Connect. Different domains can be described by means of predefined components with the system engineering simulator, the engine, after-treatment system, liquid flow for describing the cooling and lubrication circuits, mechanical domain, control functionalities, and the electric domain for hybrid models. Today I would like to have one focus on crank angle resolved real-time engine models. They are important components of system simulation because the combustion engine will remain a dominating element for the propulsion system for marine applications, for many marine applications, for the next decades, in spite of the hybridization and electrification in certain areas. The technical reason for using these models is that crank angle resolved simulation allows the description of phenomena which cannot be described by mean value approach. For example, the discontinuous gas exchange processes, pulsation effects, or cycle-resolved combustion processes. Besides, as the availability of measurement data is limited, especially for large engines in concept and layout phase, physics-based real-time engine models are of special interest in view of system simulation and model-based development approaches. This approach, which is more or less a thermodynamic cycle simulation in real time, as the gas exchange process and the high pressure cycle in the cylinders are simulated in crank angle resolution, and also the pressure and mass flow pulsations are considered. Several engine features and phenomena can be considered, such as cycle-to-cycle variations, EGR operation due to pressure pulsation, skip firing for gas engines, knocking, misfiring, variable valve timing, and dual fuel engines. We have a cylinder individual simulation, and we can use different types of injection, combustion, knock, and emission models. Such innovative engine models can be used for the simulation of the overall ship propulsion system. A model of a ship can be created with cruise M. The modeling depth of the models can be chosen in accordance to the question which should be answered by the simulation. We can use a simple map approach of the engine, or like in this case, a detailed crank angle resolved real-time engine model of a large two-stroke engine. The propeller can use the open water characteristic of a propeller under consideration of wake fraction and thrust deduction, or it can use a more simple approach. And also for the ship's resistance model, it is possible to use more physics-based or empirical approaches. With such a model, we have simulated a Supramax bulk carrier with 55,000 deadweight tonnage and an overall length of 190 meters. The question was, what is the fuel saving potential when reducing the vessel speed from 15 knots to 14 knots? It is approximately 14%. And in this simple example, we calculated also the fuel saving potential for a route from Hong Kong to Rotterdam, which is 176 tons. Another investigation was processed with regard to fouling. Due to the growth of plants and animals on the hull and the propeller, the resistance increases significantly during the operation of a ship. Here we calculated the resistance increase within 1 year, and the corresponding increase in fuel consumption in 1 year is approximately 10%. Such investigations can be performed for optimizing the dry docking intervals and the maintenance intervals. The following example of a ship simulation was used to support the efficient development and validation of a shore-based navigation system for autonomous shipping. The model is a fully functional ship simulator to be connected to environment and traffic models, and it includes detailed engine simulation in real time. The considered ship is a roll-on, roll-off car carrier with an overall length of 140 meters. It has 2 independent propulsion lines with 6,500 kilowatt diesel engines and 2 controllable pitch propellers and a bow thruster. The simulation model was set up with Cruise M. The relevant components of the propulsion system were considered, and a fully functional maneuvering model was set up. In this case, we used a kinematic model for the ship, solving the equations of motion for 3 degrees of freedom, considering also the influence of wind and sea currents. The propeller model considers the open water characteristic. In this case, the fuel characteristic of controllable pitch propellers was considered. For the engines, we used detailed crank angle resolved engine models, providing also the cylinder pressure diagrams in real time. Here you can see the speeding up of the vessel from standstill and idling of the engines. If the set point of the engine speed for the two engines is changed from idling to MCR speed, the mean effective pressure is getting higher and the engines and propeller speed increase. Based on the propeller and the ship speed, the pitch of the propellers is controlled. On the right curve monitor on the top, you can see the time-based cylinder pressure of cylinder 1. The peak cylinder pressure is getting higher and higher according to the injected fuel mass. With this ship simulator, all relevant ship maneuvers can be simulated, and so it was perfect for the development of and validation of the navigation system. As an example, the comparison of the simulation results with the measured data of the sea trial test is shown in this figure. The comparison indicates a good correlation for the speed up of the ship and also for the turning circle with a rudder angle of 15 degrees. We can also perform system simulations for complex propulsion and energy systems. Here you can see the topology of the model of a cruise liner in the Cruise M graphic user interface. The model comprises 6 combustion engines for power generation. It is a diesel-electric propulsion system. The bow thrusters and aft thrusters are also considered. Electric energy is not only needed for the propulsion of the ship, there is also a high hotel load, and such simulation models on system level allow investigations on the energy system and the optimization of the power management system. A similar figure is shown here. It's the model of a so-called pure current truck carrier, a PCTC vessel. The ship is equipped with a large 2-stroke propulsion engine with a shaft generator, which can be also used as an e-motor for propulsion. Together with the auxiliary engines for the power generation, different operating modes are possible for power take-in and power take-off. Nowadays, the application of energy storage systems, such as batteries, is being considered even for large ships for reducing the environmental impact near the coast and near harbors. We can perform feasibility studies of new innovative configurations of propulsion and energy systems. The next topic I want to cover is hybridization and electrification. In Europe, there are some market movements in this direction, mainly with founded programs and projects. The motivation for hybridization and electrification is not only the environmental responsibility, the efficiency improvements, or emission legislation. There are also other reasons, such as component protection. As an example, the peak shaving of dredging ships with sudden load steps to protect the engine can be mentioned. Additional electric motors and energy storage systems can improve the transient behavior of ships and help the maneuvering and dynamic positioning. It is also a safety topic, as redundant propulsion systems are possible. Besides, the low acoustics and thermal signature with military applications and the silence and comfort with luxury yachts are of interest. Today, almost all hybridization projects are funded by governments. Maybe this is also a good motivation for introducing electrified propulsion systems and energy storage systems for marine applications. The systems are becoming more and more complex. The number of system components and parameters is increasing. The demand for the optimization of operating and control strategies is high. Therefore, system simulation can be seen as a valuable tool for concept decision and system optimization. In the virtual world, models are indispensable components to investigate and optimize the complex interactions between subsystems. For hybrid applications, we need models for energy storage systems such as batteries or fuel cells. Generally, AVL has many different battery engineering services: design engineering, system validation, testing and benchmarking, future technologies, and many other. There are challenges for battery development on system level with the questions: can I determine the most suitable battery size for given energy and performance targets? Can I optimize the battery cooling system including relevant components? Or is it possible to reuse my models for energy and thermal management control, function development, and later on hill and test systems? So, battery models and system simulation support various battery and hybrid development activities. There are, of course, different types of models on component level, but for the system simulation, we need models on system level. The model should describe the electric and thermal behavior of cells and batteries, voltage response to current, time and temperature, heat losses, temperature and cell resistance, but also aging effects. In our simulation tools, we use empirical electrothermal battery cell models, but also a semi-empirical model based on equivalent circuits. For the description of aging effects, there is also an empirically based model with a self-training algorithm. The state of health is a function of temperature, state of charge, current, time and history. To make sure that the battery model actually describes the operating behavior of the battery, various parameters have to be set. Some of our customers had problems with the parameterization of the battery models, and that was the reason that AVL developed the so-called battery parameterization wizard. The results of our battery and cell testing, in particular dynamic data for charge and discharge at different conditions, are the input for this tool. The tool itself automatically executes the data regression to calculate the parameters of the RC pairs and the result data assembly. The results can subsequently directly be transferred to the battery model. The following example shows the application of real-time engine and battery models in a simulation of a hybrid tugboat. It can be used to support concept decisions, furthermore to specify the components of the propulsion and energy system, and another important task of the system simulation is the optimization of the operating strategy for a given operating profile. In this case, we have an operating profile with very high percentage of operating time with lowest required propulsion power, which is a good use case for hybridization. The ship model was created with Cruise M. The modeling depth of the sub-models can be chosen in accordance to the questions which should be answered by this simulation, and in this case, we used battery models describing the electrothermal behavior by means of a semi-empirical approach. For the engines, we applied a detailed crank angle resolved engine model, providing also the calculated cylinder pressure diagrams in real time. The torque for the propellers can be provided either from the electric machines or from the main engines. I would like to remark that for investigations of steady-state performance, we would not mandatorily need such a system simulation. However, for describing the transient operation and for the optimization of operating profiles, the use of such a system engineering simulator is quite helpful. the movie of the simulation shows a part of the speeding up of the boat, starting with pure electric propulsion, and the main engines are already in idling. After a while, the main engines are contributing to the overall power output, and the fraction of power from the diesel engines is increasing with the higher load demand. In the graphs, the propeller speed, the speed velocity, and the state of charge of the batteries are depicted. As a thermodynamic cycle simulation of the main engines is performed in real time, also the in-cylinder conditions are known at each time step, and you can see the increase of the peak cylinder pressure in the top right curve monitor. So this information is very useful for the control system development of the engine control system, for example. Fuel cells are becoming more and more important as power units, also for marine applications. Due to the silent operation without vibrations, fuel cells are interesting for power generation in military applications, but also in luxury yachts. AVL has developed different products in the past, such as solid oxide and proton exchange membrane fuel cells, with different properties and for different power ranges. The common thing is that these fuel cells are multi-domain systems, and therefore the multi-domain system simulation can support important development tasks. A fuel cell consists not only of the stack as the core component, but there is also the air delivery system, the fuel delivery system, the cooling with the air system, and of course the electric system enabling the energy storage. And there are various interactions between these subsystems. The objectives of the simulations are concept definition of the fuel cell, the optimization of system parameters, and the support of the integration of the fuel cells into particular applications such as yachts. As a simulation example with this model, the variation of the air pressure in the system is shown. The graphs represent the time-based results of the possible hydrogen consumption and the electric power output when changing the air pressure. Finally, I want to show you our virtual testing activities for marine applications. There's a clear added value. We can reuse the models already used for system simulation also in our model-based development approaches. Such model-based development is characterized by the replacement of hardware components by real-time capable simulation models running on hardware in the loop systems. Especially for large engine applications and their particular boundary conditions, model-based development approaches and virtual testing are of high interest as they offer several benefits. For example, testbed operation for large engines is a big effort. It can be very expensive, and also the fuel costs are in the range of thousands of euro per hour. Testing, of course, cannot be fully replaced, but the virtual approaches should support testing in the best way. Here you can see AVL's virtual test field. The operating panel is completely the same as on the real testbed. We have the testbed operating system, the automation system, and the optimizing system running, and the operator needs not to know whether he operates the real engine or a model. The tests can be automatically performed during night without manpower. Numerous tasks can be performed with such virtual testbeds and hardware in the loop systems. One main field is control system development, the development of functions, algorithms, and the controls, including monitoring and OBD. Another very important field is model-based calibration and model-based exhaust gas after treatment development. As a last example for this webinar, I would like to show an example from model-based exhaust gas after-treatment system calibration on a virtual testbed. The objective of the project was the calibration of the engine control unit in view of mainly the fuel injection parameters and the urea dosing quantity for a V12 diesel engine with a SCR system for marine application. For this task, we used again a crank angle resolved real-time engine model. This innovative aspect, or the innovative aspect in this project, was the combination of several features, such as a hydraulic rail model for the common rail fuel system, a phenomenological combustion model, simulating the combustion process and NOx formation, and besides a multiple SCR after-treatment system model. With this combination, the engine performance and the NOx formation could be simulated based on the signals coming from the hardware engine control unit. The results, or parts of the results, can be seen on this slide. In the course of this work for calibration of the control system for minimizing overall operational cost, which means the sum of the fuel and the rear cost, we could find some interesting phenomena on the virtual testbed. For example, the characteristic of the overall operational cost dependent on the injection timing, in particular operating points. We would not have expected that the overall cost would continuously decrease by advancing the injection timing as the NOx formation is increasing. However, the reason could be found in the fact that the temperature range of the catalyst inlet temperature is quite high. In this specific part load operating point, shown in this figure, the advanced injection timing leads to lower catalyst inlet temperature. Consequently, the ammonia loss is decreased, less urea is needed for the same conversion rate. So the operational cost minimum is shifted towards earlier injection timing. Please note that this is not a general trend. In total, the new calibration of this system leads to a cost reduction of up to 3.3% for full load and approximately 1% in the considered operating cycle compared to the baseline calibration status for the engine without an SCR system. As a conclusion of this webinar, I would like to say that system simulation and virtual testing help to understand complex marine applications and help to optimize performance and operating strategy in view of low operational expenditure. There's a big potential in reducing cost and development time. Besides, the methodology is a clear measure of quality assurance. With the implementation of real-time engine models with crank angle resolution, the performance of engines within the overall system can be described in a very detailed way. That means that combustion engines can be optimized for hybrid operation in order to increase the overall system efficiency. AVL expects in the future an increase in system simulation and virtual testing, even in a way of permanent vessel optimization by means of models during ship operation. Thank you very much for your attention.